It's almost half of section 4.2. So basically what we're going to say, am I on air? I'm on air, but I forgot to put off the video. Lovely. Okay, so directed graphs, we're skipping the last part, this very horrible algorithm that I can't even pronounce the name. So 584 to 594, we're not doing. Okay? You don't have to prepare that for the practice. All we're going to do is have a look with the directed graphs is how do things change when I move from an undirected graph to a directed graph. Right? So with the undirected graph, you have two nodes and you have a line between them. That means there's a relationship, but it's not a directed relationship. Okay, it's like friendship. Undirected graph is friendship. If you're one of my friends, then I'm one of your friends, right? Undirected, both directions simultaneously. If it's a paternal relationship, you are your father's son, that does not mean you the father of your father, right? It only goes one direction. So if the relationship is father-son, then clearly it's a directed relationship. You can't just turn it around. Okay. So let's have a look. Exactly what is a directed graph? A directed graph is simply a set of vertices and edges, but in this case, every edge has a start point and an end point. And the meaning is that the edge goes from one node to the other node, okay? Not the other way around. So when we look for paths, for example, if I have nodes A, B, C, and A is connected to B in that direction, and B is connected to C in that direction, then there is a path A, B, B, C. So there's a path, a directed path from A to C. However, if I have a node A goes to B and C goes to B, then there is no path from A to C. Although they are connected by edges, it's directional, so I cannot go from B to C, therefore there is no path from A to C, right? It's all fairly obvious. Everybody happy with that? Okay, right, so let's see. Directed path, directed cycle, same definition. There's one directed path and directed cycle, same definition as for undirected, only you may only follow the direction of the arrows given. Simple path, no repeated vertices. Okay, length of a path, number of edges. That's all the same as undirected. The question becomes, do we have something else? And in this case, in the beginning for the directed graph implementation, we keep it as is. Okay, so at edge, we will have the adjacent vertices. And again, you have different choices of input, all the same. The only thing is give me a vertex W and a vertex V, and if there's a edge from V to W, then I add it to the adjacency list, but not the other way around. Okay, so here is your typical representation with the adjacency list. Okay. So, for example, remember that with the undirected graph, if I had a link 7 goes to 6, then immediately I would have had 6 goes to 7, right? Because it's undirected. In this case, that does not happen. Okay, and therefore the input that you give the graph is very important. If we use this standard way of doing it with integer space integer, then that means directional from 4 to 2, not the other way around, unless somewhere I also get a 2 goes. Okay. And it's all the same, the reachability, all the same, all the same. Question becomes, how do I mark? If I do my depth first search, will it still work exactly as in the unmarked case? Yes and no. There's a slight difference in the algorithm that you have to be aware. So in this is the example from the undirected graph, but now you can see we added directions. So for example, if I am at node 0, I can reach 5 and I can reach 1. Yes, but I cannot reach 2 and 6 because actually the directions go there from 2 to 0 and from 6 to 0. Okay. And then we do our usual thing. From 0, I choose my first adjacent node, which is 5. So I go to 5, I mark it as having been reached. And then I would need to go further. Look at the red arrows there. Let's move out a bit. Yes, so from 0, I go to 5. From, given the red arrow there in the example, now I am at 5, so I go to the first link at 5, which is 4. I go there, I go to 2. And now, if I am at 4, my first link is 3. And from 3, I can go to 2. And from 2, I would want to go to 0, right? But I don't because it's already been marked. Okay, and so on and so forth. Okay, so there is nothing strange there. The only thing that is added is there is the concept of a directed cycle. If I don't have a cycle in a directed graph, it's known as a DAG, a directed acyclic graph. And directed acyclic graphs are fairly important because we can use them for all sorts of applications where we know there should not be a cycle. Okay? And the most important, there's a few examples. Job scheduling, course scheduling, inheritance in Java, symbolic links, and so on and so forth. You know about symbolic links on Linux? Yes or no? If you don't, find out, please. It's one of the nice things that Linux has over Windows is this whole concept of symbolic linking. So please do me a favor, that's one of those little old bonus questions that come up in the tests. Yes? Did you like your bonus question on Friday? Okay. So scheduling, as you may know, is a difficult problem to solve in practice. Yes? Even with the cleverest algorithms, scheduling takes quite a long time to solve. Imagine simply the university with all your subject choices, then lecturers that are available to give those subjects, rooms that are available for that specific course of sufficient size, and so on and so forth, and put all those constraints down and try to figure that one out. The most difficult thing I've ever tried to do in all my years at the university is to change the WIF roster. And actually, when we want to introduce a new course, the first thing you fill in on the form is there is space in the WIF roster. And if there is no space in the WIF roster, there is no ways that you will be able to change anything to any course, never mind the academic merits. That thing is an absolute monster. And the reason being that scheduling is a well-known, very not difficult, it's just you have so many options, right? So to balance all those options is very time consuming, okay? So scheduling is one of my favorite problems. And there is something called precedence constraint scheduling, okay? Precedence constraints, that's something if you're a project manager. Not that any of you now think you will one day in your life become a project manager, but trust me, if you work through bureaucratic hierarchy, you might someday be in a company where you started your own programming company and the thing is exploding and now suddenly you're employing 60 people and you've got this huge project and you got a large corporate client and now this thing is just running away from you. Suddenly it's not just me on my laptop doing my undergraduate programming. Suddenly there are 60 people involved in this project. How do I manage it? And the big thing with project management is what must be completed before I can start something else. Because clearly you want the project to finish as soon as possible. So things that can run in parallel should be done in parallel, yes. But then there are these dependencies. So what can I put before something else? Okay. So if you can model this as a directed graph, so there's an arrow from A to B if A must come before B. And therefore a precedence precedes. Whatever. Die een moet voor die ander een kom. Just see. I don't know how you can learn anything in this course with my language abilities. Okay. Now I can't remember how to say it. The P constraint scheduling problem. What are my constraints? What must come before everything else? Okay? And if I can do that, if I can write down my problem as a directed graph so that I know what must come before the other, yes, and then order this graph, walk through this graph in the correct order, then I solve my problem. Okay. So you get the idea of the topological order, yes. What you basically do is you say A must come before B. I must do algorithms before I can do theoretical computer science, but before I can do theoretical computer science, I must also do linear algebra and so on. Otherwise, you can't solve your lovely recurrence relations, yes, and so on. Okay, and then if you draw that up as a directed graph, and it is possible for you to walk through it in reverse order. Why in reverse order? I want to put it down so that I can see what must be really first. And then if all the arrows are pointing down, that means I have what is known as a topological sort. Yes. I was able to write down the directed graph so that all the arrows point down. Yeah. Then it is possible to use this for my scheduling, for my project management, and incidentally for sorting. Okay, so there's your definition. Directed acyclic graph is a digraph with no directed edges, and your code. Okay, which I'm not going to go through. Basically, what you want to do is you want to walk through your directed graph depth first, and then you can either have a pre-order or a post-order or a reverse post-order. So the reverse post-order is the one we're looking at. Pre-order says, let me go back one step. If I have a directed graph, yes, and I know it contains no cycles, it must be a DAG, then I can start, and as I visit the nodes, I record where I am at the moment. That is writing down the results in pre-order. Or the other way around, the moment I'm finished, yes, you can see here, I started at 0. From 0, I go to 5. From 5, I go to 4. Now I must stop, and my recursion bubbles back. Yes? So if I record my nodes in the order of getting there, I get the pre-order. If I record my nodes at the point where the recursion stops and bubbles back, that is post-order. Does that make sense? Yes, I still visit in the same order. It just depends where I note where I am at the moment, right? And then the other thing that we can do is reverse post-order. That's somewhat strange, but think of pre-order and post-order as keeping a queue of where I record my nodes, yes. The reverse post-order then basically takes post-order, but I record it in the reverse order. So I put my things on a stack instead of on a queue. Remember with the queue, yes, queue I put in front, with the stack I put on top. Okay, so I put at the back, as it were. So if you look at this output, here I would record a 4, that's fine. Over here, I would have 4 and then 5. And then my reverse post order would show 5, 4. Yes, so this output here is exactly the reverse of that output. So if you understand pre-order and you understand post-order, you can basically write down the post-order and just write down the nodes visited in the reverse order. Okay, it's just how I write down where I'm visiting. Yes.
Can we do this using vector search?
What would that give you? Would that give you? I think that would break the direction somewhat. So let's think quickly, the question being, could we do topological sorting using breadth first instead of depth first? So what, instead of getting 0, 5, 4 as with depth first, we would get 0, 1, 6. Sorry, 0, 5, 0, 1, 0, 6. So we would get 5, 1, 6. And what does that tell us?
Oh, because you wouldn't be able to get to, how do you get to 2, 3 at all? Where do they do that?
Oh, that, thank you.
They don't do the depth either. How do they get there?
Did anyone catch that? Yes? Do you all see the problem? Look at this directed graph. It's got zeros connected to 6, 6 to 4, zeros connected to 5, 5 to 4. Hang on, what's going on here? 2 is connected to 0 and to 3 is to 5. But if I follow the path from 2 or 6 or wherever, this, I cannot reach this because the directions are wrong. Do you see that?
But they then check it, they check from there as well later.
Yes.
They check here and they check two.
Thanks for picking that up. So what the algorithm does is, if I come to a point, if I get to a point where I have finished all my directed edges, they look at where the edges are, the nodes are marked as having been visited. And if there are any unvisited nodes, they simply plunge in there.
And so you could use breakfast as well.
I'm just wondering what breadth first will tell me about precedence. So what comes before that? Let me think about that, and we can talk about that again on Wednesday. What is the difference between, if I want to do a topological sort, I now know because the book told me that I can do depth first search, right? So the question is, what would be the difference in the output, and what would it mean in terms of scheduling or precedent scheduling? Is it still a topological sort if or would there be a specific application that could use breadth first instead of depth first? And I have no quick answer. So please send me an email, otherwise I'm going to forget. Just send me an email and we can have a look at that one on Wednesday. Okay, right. No propositions.
There's a breakfast on page 573.
No, there's not.
So in the problem it says single source shortest directed path, solution breakfast directed path, page 573.
Well, page 573, I'm looking at it, finding paths, single source directed. Where do you see that?
In finding paths and diagrams, it says depth first paths and breadth first paths, and that's on page 540. The algorithm.
Yes. Yes. So basically all they're saying in that sentence is breadth first search as given will still work in a directed graph.
But isn't it only of the directed graph that's two arcs in each?
That is?
If it's two directions between each vertex.
No.
I mean, breadth first search working if it's because undirected graph is basically two directions.
You would still be able to push onto the queue with breadth first, even if it's only one way, I think. Mr. Walmart.
How would it handle like a case where the two would be unconnected though, if it was a first search?
Well, the same way it doesn't do it, you just add it to the end.
Yes.
It just pops it on.
But yeah, but surely you'll go to a first search will go search through and you'll say, oh, that.
No, because it has a list of the nodes. That's why.
It marks the nodes, yeah. So it goes back to the list of marks, or the, what is it, the stack or a queue, I can't remember. But your collection of unmarked nodes. So when you finish and there are still nodes that are unmarked, it simply tackles them one by one.
Yeah, but that's not handled by the depth search itself, that's handled by your code that uses the depth search. Because
yes.
doesn't contain it, yeah.
Yeah. Okay. Reverse post order, and that is it for directed graphs. Okay, so there are no proofs. The idea is that for directed graphs, that We can do depth first search and we can do breadth first search in directed graphs. Just remember you now have a direction, right? And then when you stop the recursion, exactly how do you bubble back, okay? And the whole issue, if you have a directed graph without cycles, that is a thing called a DAG, a directed acyclic graph, and we can use the depth first search and maybe breadth first search in a directed, in a DAG, to do topological sorting. Topological sorting is used for scheduling problems of any kind, where you have constraints where one thing must happen before another, okay? With very, very practical applications, okay? And there are no propositions that you have to know, and you can leave out the last part of the section on the connectivity. Okay, which brings me to a minimum spanning tree. Okay, so today and tomorrow, indeed, still today. Today and Wednesday, we will try to finish minimum spanning trees, right? Because I'm rushing through a bit because your practical test is on sections 4.1, 4.2, and 4.3. So we have to cover all three the sections completely, and I don't want to finish Thursday morning at 8 and you're writing on Friday. Okay, so I do apologize for the somewhat rushed presentation, but there really is not a lot to directed graphs apart from the topological sort. Okay, so what we now add, we had the idea of the undirected graph, then we had the idea of the directed graph, and now we come to something which we call an edge-weighted graph. And these things are tremendously practical with lots of applications. An edge-weighted graph is simply the idea that I have a graph, but I assign a weight, a value to every single edge. Okay? It can be undirected or directed. Again, the directed is simply a fairly easy extension of the undirected. So for these edge-weighted graphs, we are just going to cover the undirected version. Okay? It's not difficult to go to the directed. Now, where would that be an issue? Any optimization problem that you can think of can usually be modeled with an edge-weighted graph. For example, I have a map. I have a company rep who wants to travel to different towns to visit them, look at the shops, and he wants to minimize the distance that he travels. Incidentally, do you recognize that as a known classical problem? Which is? Traveling salesman problem. The traveling salesman problem is also NP complete. Are you familiar with the term NP complete? Heard about it? That means it's bloody difficult. And it takes a long time. Difficult in the sense that the solution is very easy, but up to now, the only known solutions are exponential in time complexity. Okay? So the only known solution is basically brute force. You visit all possibilities, therefore you get an exponential solution. There are no known polynomial solutions. In time complexity theory, we remember as we went through sorting and searching, I kept on hammering that, yeah, linear is fine, exponential is bad, logarithmic is good. Yeah, so that's a kind of thumb-sucking judgment that you can pass on an algorithm. So what the theoretical computer scientists do is they say, if I look at computation, there are algorithms that will not have a worse than polynomial solution. Okay, I'm really hand-waving because I'm not doing the theory. But basically, algorithms that will have, might be badly polynomial. Yes, it may be n to the 5217, but it's polynomial. Yes. Inherently, there will be a polynomial solution. That is the class P. Then there is another class of algorithms called NP. NP stands for non-deterministically polynomial. But think of it as not polynomial. These things always have an exponential time complexity, and the traveling salesman is one of them. In your honors year, in your 4th year, you get to problems. No, wait. In your 1st year, you hear that there are problems to be solved, and I code them with an if and a for loop. And then in your 2nd year, I say, wait. Don't hurry off. There are good solutions and bad solutions. Yes, the bad solution is the one that takes too much time or uses too much memory. And then the good solution is what we want in the theory of algorithms. We want an algorithm that will be time efficient, okay, and memory efficient. And that is what you spend such a lot of hours on this year. And then in your 4th year, we stop and we say, well, are all problems even solvable? And of course, they're not. There are problems where you cannot write a computer program to solve the problem. And if you are interested in that kind of thing, where are all my theoreticians today? I miss my math majors here. Are you writing tests? Is this the... Okay, so the theory here is you can have a look on Google at the domino match problem. Basically, whenever you have an infinite number of possibilities, you cannot write a program to solve the problem. Because if you have to check all the possibilities, if after 3.5 years your program hasn't stopped yet, you do not know why. You do not know whether that is because there does not exist a solution or whether you just have not reached the solution yet. So there are problems that are not solvable by computer, unless you restrict the infinite number of possibilities. Same argument.
Then what's the other problem? It's impossible to solve. Why would you say, okay, I'll tell you what, let's solve this thing with infinite possibilities? It's like writing infinity and trying to write out the infinity.
Basically, let me give you an example from the domino match problem. It's a very simple thing. It says, imagine dominoes, instead of those dots that they have, which represent a 3 or a 5 or a 7, you all know what a domino is. Yeah? Nee man, deesdae speel hulle mos net World of Warcraft. So a domino is a block with 2 sides, and normally there are dots here representing a number. I'm saying that I'm going to put letters from the alphabet there. And the letters from the alphabet that I put down, I can put either 1 or 2 or a finite number of letters there. And the domino match problem says the following. Is there any possible way that, given a finite set of dominoes, that I can put them next to each other, yes, so that the string at the top is the same as the string at the bottom? But how does that represent an infinite number of possibilities? The thing is, I can reselect another domino. Yes. So I can choose any one of these dominoes more than once. Okay. Any number of times that I want. So there comes my infinity. Any number of this set of dominoes put next to each other, does that give me the same string at the top as at the bottom? We have a slight problem there because the A, B, C, but then I can get C, A, B if I put the second one first, but then my bottom is in the wrong order. So given a set of dominoes, you can try to do it by hand if the set of dominoes is not very large, or you can give a calculated argument on why it would be impossible for a given set of dominoes. But to write a program to do this, it just doesn't roll if your set, or to do it by hand, if your set becomes too big, the possibilities are just too many. Because I can choose the dominoes any number of times that I want. I can repeat the domino as I want. Okay? And this maps to many practical applications as well. So read up a bit on the domino match problem, and we can talk about that on Wednesday as well if you want. Okay? So I've now drifted far away from where we were. Let's come back. To the traveling salesman problem, which is an example of an NP complete. NP complete means it takes long to solve. But you need to be aware of that. You also need to be aware that some problems cannot be solved. Okay. Right. So back we are to the minimum spanning tree. Okay. That was traveling salesman is an example of such a problem. It is an optimization problem. So almost any optimization problem can be modeled in terms of an undirected graph, or directed if you want, with weights on the edges. Incidentally, speech recognition is also modeled using this. Okay, a bit of a far jump. If ever you hear Prof. Niesler from E&E give an introductory talk on speech recognition, do go and listen. It's absolutely fascinating. If you think about stats, yes, probabilities, you can put probabilities on these edges. And then you can try to minimize or maximize, as it were, whichever direction you want, on what path would be best to follow. And this is how it matches to speech recognition. If you hear a word, the word must be broken down morphologically into its different syllables, but you don't necessarily hear the syllables, right? To know what the word is, I have to break it down into syllables, right? Lecture, okay? Lecture. But you don't necessarily, in order to recognize it, the speech recognition means take the sound and break it, put it into text. So how do I spell the word? How do I find it in the dictionary just given the sound? You have to break up the sound morphologic so that you get the morphological components of the text word, right? But as you know so well in English, or in French is even worse, yes, because you don't pronounce what is written there, mostly. So that is a difficult problem, and what you can do is you actually put probabilities on graphs like these and then find the minimum spanning tree so that I can follow the path, or the maximum, as it were, so that I can maximize the problem, follow the path with the highest probability of being the correct one. Okay? So on Wednesday, we'll tackle minimum spanning trees, and we will cover two algorithms called Kruskal's algorithm and Prim's algorithm. Okay? And then we're ready for the practical test.